Okay, so the next two applications, C and D, are kind of add-ons to slides and ladders in many ways. Okay, so in previous examples, we all seem to have an excess reagent. So, for example, when we burn something, the oxygen in the air never runs out. But that's not always true. Okay, so say we have a reaction where it's not burning, we put a couple of things in a test tube. Which one runs out first? Which one's left behind, if you wish? Okay, so a good way to think about the concept of this is with something simple, which is like making a sandwich. All right, so here's a very, very simple kind of analogy. All right, so let's pretend we're making sandwiches, yeah, and we look around the kitchen, and we got some ham and we got some bread. Okay, you can kind of write a recipe or a balanced equation showing how to make a sandwich. Okay, so the reactants are 1 piece of ham and 2 pieces of bread, which makes one sandwich. This is of course an English ham sandwich, which has 1 piece of ham. If we were in America, it would be 14 pieces of ham, but no, this is an English sandwich. That's a joke, okay? All right, now, that's our recipe, that's our balanced equation. Okay, so to kind of illustrate this concept of limiting reactants, let's think about sandwiches. So, question, how many sandwiches can you make from 5 pieces of ham and 18 slices of bread? So I haven't got 1, I've got 5. And I haven't got 2, I've got 18. Now just think about that, right? Just think about that. Just common sense. How many sandwiches can you make from 5 ham and 18 pieces of bread if you need a 1 ham for every 2 bread? If you said 10, you'd be right, right? No, sorry, you would not be right. I'm just thinking ahead. Okay, so it's actually 5, isn't it? Let's just think about that. You use 5 ham and 10 from the 18 bread to make 5 sandwiches. 5 reacts with 10 to make 5. Because it's in the ratio, 1 reacts with 2 to make 1. Okay, so you make 5 sandwiches. Okay. Now, when we get into kind of chemical reactions, we have to use some terminology. And the first one is excess. We saw that term before. Excess literally means, it's kind of short for excess. Too much. So what is there too much of? What didn't we use all of in our recipe here? Well, we didn't use all the bread, right? We used 10 out of the 18. Okay, so bread is the answer. Okay, which is the too little of? We call that the limiting reagent. So we have excess and limiting reagents. Which one runs out? So excess, which one is the too much of, stuff left behind? Which one do we run out of? Well, it's the ham, right? Once I've used my 5 hams, I can't make any more sandwiches, right? So it's the limiting reactant. Okay, ham runs out. That's a good way to think about it. The limiting reactant runs out, it limits how many sandwiches you can make. I can't make any more sandwiches once I've used all my ham, okay? And that's the limiting reactant. Ultimately, which ingredient determines how many sandwiches? Limiting reactant, which in our case is the ham, okay? Once I've run out, I can't make any more sandwiches. Now, we kind of answered this already. How much of the excess reagent is remaining? Now think about it. I use 1 ham and 2 bread slices for a sandwich, right? So when I've used 5 ham, I've used 10 breads. And then I can't make any more sandwiches because I ran out of ham at that point. Okay, and I leave 8 behind. Okay. Which reaction, sorry, how much of the excess is unused? 8 slices. Bread, if you think about that, use 10, leave 8. Okay, so we need 10 slices to go with, of bread to go with 5 slices of ham to make the sandwiches, so we leave 8 behind, just so you can see it. So 8 slices of bread left behind, unused, because we use 10 and leave 8. Okay, I hope that makes sense. So that's the concept, all right? So what we're going to do is something very similar, but instead of sandwiches and bread and ham, we'll just use formulas, okay? So it's the same concept, okay? So we're going to think about limiting, excess, etc. in terms of things in the test tube now, okay? So The balancing numbers in a chemical equation, the stoichiometric factors, are just like the numbers of slices of ham and bread, right? And sandwiches, yeah. So, before it was 1 ham and 2 bread makes 1 sandwich. Here we have 1 reacts with 1 to make 1 and 1. Okay, so it's the same kind of idea. So if you think about it, if we want to be perfect, if we want to be absolutely perfect, we put exactly 1 mole of this in a test tube with exactly 1 mole of this. They react in a 1-to-1 way to make products and nothing's left behind. There's nothing excess and nothing limiting. But think about that. You think you can actually put exactly 1 mole of stuff in the test tube? No way, right? Because you'll need 6.02 times 10 to the 23 things counted exactly, right? My calculator goes to like 8 decimal places, not to 23, right? So there's no way you can physically measure to the accuracy needed to get exactly 1 mole. Okay, so no way, all right? So there's always going to be, no matter how hard we try, there's always going to be too much of one thing, which is the excess reagent, like the bread in the previous example, and too little of the other. If there's more than one, there's less of the other, right? So that's the limiting reagent, okay? So there's always too much of one and not enough of the other if we're putting 2 things in a container and they're both reacting, okay? So let's think about that. If I have 10 moles of this guy, I've got 10 of those, all right, and 15 of these. It's just like the sandwiches again, right? Which one is there too much of? Which is in excess? Well, 1 reacts with 1, and I've got 10 and 15 in the jar, right? So obviously 1 reacts with 1, 10 would react with 10, but hey, there's 15 of this guy, right? So there's too much of that. So it's NaCl. Right? Which is limiting. You can kind of glass half empty, glass half full. There's 15 of this, and in a 1-to-1 ratio it needs 15 of this. It's not enough. So it's the other one, AgNO3. Right? How many moles of AgCl would be formed? Now think about the sandwiches, right? 10 would react with 10 to make 10 and 10, because 1 reacts with 1 to make 1 and 1. 10 would react with 10 and leave 5 behind to make 10 and 10. All right. Hey, as we just mentioned, how many moles of NaCl would remain unreacted? Well, hey, 10 reacts with 10 from the 15 to leave 5 behind. So 10 used, 15 left. That's what I like to call the true excess. The true excess is the actual number left behind, okay? So 15 obviously is too big because we need 10, but from that 15 only 5 is kind of left behind, so that's like the true amount that's left behind. Okay, so our trick was what? We compare what nature gives us, which is the 1-to-1 ratio. 1 reacts with 1. It's all about the reactants, remember, okay? 1 reacts with 1, so 10 would react with 10. Okay, but we don't have 10 and 10 in there. We have 10 and 15. Too much, not enough. Okay, so compare the ideal ratio, 1-to-1, from the balanced equation, with the actual ratio, what you throw in a test tube. Now remember, you can always work out how many moles are in a test tube because grams, molecular weight, and moles, right? Okay. Since the limiting reactant runs out first, and this is very much a key statement here, since limiting reactant runs out first, it determines how much product you make. So if you think about that, once that ham ran out, we couldn't make any more sandwiches. That's why we made 5 sandwiches, right? Because there was no more ham left. So once our limiting reactant is exhausted, we can, if you like, slide across in our slides and ladders, and that determines how much product we make. Okay, so we'll see this as we do the questions. Bottom line is this: once you determine, just through observation typically, which is the limiting reactant, that's the one we'll slide across with to make our products. Okay, so it's a little twist on slides and ladders. Essentially, we have this extra step where we determine which one we slide across with, and the one that runs out first we slide with. Okay, so let's try a couple of questions. So now remember, we're never going to get the exact ratio we want, okay, because there's just no way we can measure exactly 1 mole or something. Okay, so to be honest, we don't even try. We just throw some stuff in there and do the math. Okay, So typically we do something like this. So work out the mass of each product formed in the following reactions, assuming 10 grams of each thing are thrown in, okay? So 10 grams of this, 10 grams of this, we'll do the math and figure out what we get over here, okay? So same as the slides and ladders, but we're gonna have to work out how many moles of each reactant and then make a decision which runs out, okay? So you can look up the various numbers for molecular weights and stuff, okay? So I don't want to burden you with that right now, but feel free to just try it if you wish, okay? So let's fill in what we got. 10 grams of each reactant. And our theoretical yields are in the same spot as normal, right? Molecular weights, you can work them out, okay? This is 169.9 grams per mole, Ag, N, and 3 O's. Okay, NaCl 58.45, that's like 23 and 35.45. This guy 143.3 grams per mole, and finally NaNO3 85. Again, you know, feel free to pause that, and if you want practice working out these molecular weights from formulas, you know, feel free to do that. But hopefully you're okay with those numbers. All right. Now remember, molecular weight, grams and moles. The legendary triangle is always going to help us out, right? Okay, so moles is grams divided by molecular weight. Divide to go down, so do it for both. One of them will be excess and one of them will be limiting, right? Here we get 0.0589 when we divide those numbers. Here we get 0.171. Okay, now it's kind of obvious which one's too big and which one's too small there. Okay, but I want to show you a little trick because sometimes it's not obvious, right? What I like to do is this. I like to cover one of them up, okay? And I say to myself, hey look, one of these reacts with one of these. So to be perfect, 0.171 needs exactly 0.171 moles, right? That's if it's perfect. If this number under my finger is bigger than 0.171 in a 1-to-1 ratio, if it's bigger, it's going to be excess. If it's smaller, it's going to be limiting. We figured it out. So that one is limiting. That one is excess. You can go the other way too. You can say to yourself, well, hey, how about that? Oh, let me come the other way here. What about that? 0.0589 in a 1-to-1 ratio to be perfect needs 0.0589 under my finger, right? But hey, look what's under my finger. Is it bigger or smaller? It's bigger, so it's too much. Excess. So this will run out first. This is the one we slide across with. Okay, now this nice easy example, one reacts with one to make 1 and 1. What that means is 0.0589 reacts with the same amount, 1-to-1 ratio, 0.05189 from the excess to make, guess what? 1-to-1 to 1-to-1, that same number, 0.0589. 0.0589. All right, we've multiplied by 1 each time because it's a 1-to-1 ratio. We're sliding across with the limiting reactant because that's the one that runs out first. That's our ham in this example, if you remember the sandwiches. All right, so divide to go down, multiply to go up. Nice and easy. 8.43, 5.00 grams. Okay. There we go. So that's your first limiting reactant problem. Okay, now if you notice here, right, the reactants weigh 20 grams, right? But the product's 8 plus 5, all right, 13.42. So the products weigh less than the reactants. How can that possibly be? Oh, well, remember, we didn't use all this. We didn't use the whole 10 grams, right? If you actually want to work out how much of this was left behind in grams, you know, you just use the remainder from 0.171 and work out the grams used, okay? But that, you know, not the goal of the exercise here. The goal is to figure out this. All right. Okay, so I recommend a pause, all right? Try the next one. There's that favorite equation of mine with the nice easy numbers, okay? If you want to look back and look at the molecular weights, you can, all right? So again, grams, molecular weight, moles. We balance it with a 2 there, remember, it's that same equation from before. 10. Oh, 10. One big extra. What's that? What's that? What's that? We're going to have to fill in actually the whole grid to do this, which is okay, right? If you remember from before, molecular weights were 100 grams per mole, 36.45 grams per mole, 111 grams per mole, 44 grams per mole, 18 grams per mole. Okay. Divide to go down. 10 divided by 100. Nice easy number. That's why I like this one. 0.1, right? Okay. 10 divided by 36, 0.274. Okay. So now we have to make that decision. Which is limiting, which is excess. Okay. Now here's the thing. Let's do this. This time it's a little trickier because that's number 2, right? Careful there. That's 1. That's example 1, right? So one of these reacts with 2 of these to make 1, 1, and 1, right? So if I cover that guy up there, 1 reacts with 2. So 0.1 needs something twice as big, which is of course 0.2, right? Yeah. So when I remove my finger, if the number under my finger is bigger than 0.2, it's excess. If the number under my finger is less than 0.2, it's limiting. What is it? Excess, right? Now be careful, and that makes that limiting. Be careful. It's not excess just because it's bigger. It has to be twice as much or more to be excess, right? So for example, if this number here was 0.174, let's pretend it was that, right? So I say, hey, 0.1 needs 0.2, but I've really got 0.174. It's not 0.2. It's a bigger number, but it's not big enough, okay? So be careful. It's all about the ratio. It has to be twice as big because it's 2 to 1. Okay, so 0.2 makes it bigger, and then the extra 0.074 is the true excess. So you can think about that. So that's the 0.2 plus the 0.074. That's that true excess we talked about earlier, okay? So limiting is the one that runs out. That's the one we slide across with. That's the whole point of this exercise, to figure out what's limiting. Okay? When we slide across, it's easy. 1 reacts with 2. 0.1 reacts with 0.2 from the excess. Leaves that little bit behind, right? And it makes 1 reacts with 2 to make 1, 1, 1. 0.1 reacts with 0.2 to make, hey, 0.1, 0.1, and 0.1, because hey, limiting is in a 1-to-1 ratio with the 3 products. Okay, that makes the math easy. 0.1 times 111 is 11.1 grams. 0.1 times 44 is 4.4, and 0.1 times 18 is 1.8. Again, the reactants weigh more than the products because again we didn't use all of this. Okay, if we want to do a quick side calculation, right? So I've got 0.074 moles left, right? Okay, and if I use that to go up, yeah, so if I go 0.074 times 36.45, that'll give me how much I didn't use, if you like, right? So 0.074 times 36.45 equals 2.6, right? So there's actually 2.7, if I show you the calculator, approximately 2.7 grams unused. So I really used, take away 2.7, 7.3. So I really used 7.3. So 7.3 and 10 is 17, 15, 16, 17. So 17 and 17. Okay, now that's, you know, a small detail that kind of just makes sense if it was bugging you, but remember the whole point is what we did initially. Climb down, look at the ratio, find out who's limiting, slide across with the limiting and the ratio, climb back up. These are, again, theoretical yields, but they're a product of this limiting reactant scheme, okay? If we combust in air, air never runs out, so we never have to do this because it's always going to be excess, right? It's always going to be excess. But when we put 2 things in a test tube together, throw 10 grams of each thing in there, we have to do this math to figure who runs out. Okay. Now, the last application is concentration. Okay. Now, maybe this is more applicable now than ever, right? So I always do this kind of little jokey kind of preamble, if you wish, to this last application of moles, grams, molecular weight and things, okay? So let's pretend, right? Pretend you're all over 21 and after this class, you need a drink, right? So when you finish this class, chances are good you'll head across to the local bar for a well-deserved adult beverage. Okay, let's assume you're going over the road to Heroes, right? Heroes West, and they know it's chemistry day, right? So they have a special. You can have either a pint of beer or a pint of wine for the same price. Which do you choose? Obviously, given your state of mind, either you're really happy or really sad, you're commiserating or celebrating, you just want to get totally messed up, right? So what are you going to do? Okay, now, so you're going to choose the wine, right? Why are you going to choose the wine? Because wine is stronger. Wine's a stronger drink than beer, right? Why is that? Well, you just look on the label. Wine's 15% alcohol by volume, beer is 5 usually, right? Okay, so there's 3 times more alcohol in the wine. Yeah, so I'm going to draw a bunch more dots, right? That's alcohol molecules. Okay, so wine is stronger. Now, in chemistry terms, we say it's more concentrated. Concentrated is stronger. It means there's more molecules of interest, alcohol, per unit volume per pint. Okay, that's a nice way to think about it. More alcohol molecules per glass, right, is a higher concentration. Now in chemistry, of course, we don't actually count individual molecules, we use moles, okay? And we don't use pints, we actually use, if you remember, liters. So here's our deal, all right? So concentration is called molarity, symbol big M. Now be careful, that's an uppercase M, not an italicized. You know, there's 300 symbols and 26 letters, so we've got to do double duty sometimes, okay? So that's not molar mass, that's concentration. And it's the moles of solute, that's in our case the alcohol, right? Per liters of solution, that's per beer or wine, okay? So it's how many molecules in terms of how many moles of stuff in a liter of final mixture, a final solution. Okay, so there we have it, okay? That's what concentration is, molarity. It's moles of stuff, the minor component, there's less alcohol than water, right? In the entire final mixture, and the units are moles in the liter or just big M. You may have seen in the lab, for example, little bottles with 6M HCl or something. That means 6 moles in 1 liter of final mixture to make that solution. Okay, so a solution is a solute, the minor component dissolved in a solvent, the larger component. So typically that's water, right? So Pepsi, if you think about it, what is it? It's sugar. We dissolve sugar in water to make a solution. Wine equals alcohol plus water. Okay, so sugar and water combined is a soft drink, alcohol and water combined is an alcoholic drink. Oh, leave that up. Sorry about that. So wine is alcohol plus water, solute, solvent, solute, solvent. It's what you dissolve in a solvent to make a solution. All right, so now, in terms of a worked example, okay, I would typically, if this was in class, I'd do an actual demonstration. I'd pull out a sugar packet, I'd dissolve it in water, and we work out the concentration, okay? Now, here's a big trick, okay? Remember the triangles? Molecular weight, grams per mole. Fantastic, right? That's useful if we got a solid, because, you know, we weigh things on the balance of the solids, get the grams, right? If we got stuff in a beaker, we can't weigh a beaker full of liquid because a solution by definition is mostly water, mostly stuff we're not interested in. In that case, we have the strength, think of the units, concentration is moles per liter volume, okay? So that's a new triangle, right? So the concentration is moles per liter. Moles, and this is the classic you'll see in the book, moles is CV, so that's the one we use the most. If you want to work out how many moles of something are in a solution, it's its concentration times its volume in liters. And volume is moles divided by concentration. Okay, so we can use these two special kind of triangles to get around our kind of conversion planning. Okay, so let's look at this. So what's the concentration of a solution made by dissolving 2.845 grams of sugar in water, making the final volume 150. Now, the good news is we kind of did this before, right? Okay, so let's think about this. This is called making it up to the mark, right? So we put our sugar in the bottom of a container, right? So we've got 2.845 grams of sugar, C6H12O6, yeah? And if we do that, therefore we can work out moles of sugar. Remember, molecular weight, grams and moles. Moles is grams over molecular weight. 2.845 grams over, this is the same sugar we used before, 180.2 grams per mole. Still a quick calculation there. 2.845 divided by 180.2 equals 0.0158 moles of sugar. Alright, so it's 0.0158 moles of sugar in this beaker, right? Then I add water up to the mark, 150 milliliters, and it dissolves, right? The sugar dissolves when I stir it around, okay? But there's still 0.0158 moles in there. It's now just swimming around in this liquid, isn't it, right? So if I want to work out the concentration, and look what links these two triangles. It's moles, yeah? Moles is the way to go, okay? So the same moles we started in the solid are now swimming around in the solution, okay? So what's the concentration? Well, moles is CV, right? Or if you want to use our triangle, concentration is moles divided by volume. So hey, what's the concentration? Concentration, moles over volume, but that's in liters. Now be careful, it's at 150 milliliters. Hopefully you can do that now. That's 0.150 liters, right? Because it's 1,000 milliliters. So moles, same number, over 0.150 liters equals 0.105. Put M for moles per liter. Okay, that's fantastic. Okay, that's fantastic. So that's your first concentration. I'd recommend, you know, going through that once over, okay, before you try the next one. Okay, now my videos last half an hour because they kind of cut out at half an hour, and I've got 1 minute 38 seconds left. So I'm not going to start the next one on this video. We're actually have to go to another like small video just to finish the packet. And there's only, oh no, a page and a half left, right? But c'est la vie, right? Okay, but real quick, let's just go to the last page. We can now fill out that last leg of the spider, okay? Concentration, volume. Concentration is moles per volume in liters. That's what we just did. We went from grams up here to moles down to concentration volume. It's for a solution aqueous, okay, so be careful. And remember the triangle, molecular weight, grams and moles, we should maybe put there to help, okay? So that was our journey just a second ago. We went from here to here to here. Okay, that's where I stopped because the timer's about to go off. Okay, we'll show you one last example in the next video and talk about some possible exam questions. Okay, see you soon.